Hi everyone, my name is Thales Imbiriba and I'm presenting the work Enhancing Particle Filtering Using Gaussian Processes, a work that was done in collaboration with Professor Paul Closas, both of us from the Northeastern University. So we are interested in problems that are formulated in terms of state space models, such as this one given from equations 1 to 3, where we have our x represent our states and y is our observations, and p. So we have like a initial prior distribution for our states. We have a transitional distribution, and we have also a likelihood function to model our variables, our states, and our observations. So the objective with Bayesian filtering in general is to compute posterior distributions of states trajectory given the observed data, such as this one, which can be sometimes problematic if our distributions are non-Gaussian or if you have no linearity in our system. So one way to tackle this is to use particle filters. And basically what we want is to represent our distribution as a set of a linear combination of delta functions such as N4, where they are located in our state space in X case, and they will have those amplitudes W case. So these basically are our particles, which are random samples. And by doing this kind of formulation, we can easily compute MMSE and map summary statistics for our estimation of our states, as in 5 and 6 here. But particle filters have some issues, common issues that sometimes needs to be addressed. And one of them is particle degeneracy. That's during our iterations, basically one particle goes to 1 while all other goes to 0, and you kind of lose the ability to represent accurately our PDF. We may need a lot of particles to provide good estimations for our state, so good summary statistics. And also the particle filters often diverge if n, the number of particles, is small. So to address this, we basically propose to interpolate the particle filters, the particles in our particle filter using Gaussian process. And this led us to better summary statistic performance, even for smaller n, more stable implementations for a small number of particles. And also we provide a new resample strategy that accounts for the Gaussian process uncertainty. Just to summarize a little bit Gaussian process, assume that we have a training set, which are basically those balls here, little balls, so a pairs of x's and y's, and we want to interpolate them basically. And so we assume that we have a function psi, which is this embedded function, and we basically provide a distribution for this function over x. So psi condition on our training data, and for a new point we want to predict its value, we have a Gaussian distribution for this function. So for a given x here, we have a mean value and a covariance. And this mean, so we have a mean function and a covariance function as functions of x, where the mean function is basically a linear combination of kernels provided here in 8. And the covariance function is basically this equation 9. And we end up with the inference step is basically computing alpha and betas for this coefficients, alphas and betas for the GP, for the given problem. So basically alpha is this inverse times y, and betas, it comes from this quadratic form, and we can efficiently compute them using Cholesky decomposition. So our goal here is to approximate a density function using Gaussian processes. And so we want to approximate it use the mean of our Gaussian process. But to become a valid PDF, we need to ensure positivity and integration to 1. Integration to 1 is easy to impose by normalizing our mean function by this integral here. And this integral here becomes basically a linear combination of the integrals of the kernel functions. And and if you can solve this integral, we can provide an analytical expression for 10. And positivity may be enforced by wrapping the GP using some wrapping function. We didn't address this in this paper. We are addressing this in a following up publication. However, we didn't also have any big issues here because our distributions are usually smooth and not negative. They don't wiggle too much and close to negative points. But anyways, this is something that we are gonna address in the following up paper. Now we can use this GP approximation of our PDF to enhance the particle filters. So when we are computing our summary statistics, such as MMSE, we are basically solving this integral here, where we plug our estimation of PK here. And if we consider, depending on the kernel, we can solve this integral analytically as well. So we end up with equation 12, that is an analytical expression obtained when we use a squared exponential kernel function, also sometimes called Gaussian kernel. Well, for map estimation, we basically need to look for the maximum of our GP function. And because it can be multimodal, we have an initialization trick here, which is very simple. In fact, we basically look for the particle. If we assume that these balls are particles, we will basically initialize it with an X corresponding to the higher weight, largest weight we have. So we would initialize it here, and then we just climb up here until find a stationary point. And this would be our maximum posteriori estimation for the states. And just to now put everything in the context of a Gaussian process particle filter, we have present here our algorithm, where up to line 7, it's basically a standard particle filter. We generate X from this importance distribution, we propagate W's and we normalize them. And then we fit our GP by computing alphas and betas here. We compute our statistic, our summary statistics in line 9 and 10. And then we go to the resampling phase of particle filters, which we also propose an algorithm to solve it, which is summarized here. And basically what we would like to do is to sample from the mean of our GP, so to this approximation of the PDF. But because we also have this uncertain measurement measure for the GP, we were interested in using it as well, because for instance, when we have a point here that could have low probability or low mass, but when we consider also the GP uncertainty, maybe it's not that low. Here is 2 standard deviations, but if you consider 3, it would be even a little larger. So then we might be losing samples in very important locations of our function. And for this reason, we decided to also include this in the sampling, but with a given probability, we sample from the mean plus 3 sigma, 3 standard deviations, but with a, so basically iota here is the indicator function. It's 1 if u is smaller than p-var. P-var is the probability that we consider this instead of only the mean. So to summarize here, when we are sampling, resampling, we basically draw u from uniform distribution, and then we draw x from f of x. To exemplify this in the context of an application, we basically have a target tracking problem here, where we have our true target moving, and this is a non-linear, so the observation is, there is a non-linear function when we obtain the measurements, but other than that, everything is Gaussian. And we can see that the performance of our Gaussian process particle filters were better, especially in this region, but this is just one run. And when we go to Monte Carlo simulations, we can really see, a big difference in the performance and we are varying the number of particles. And we can see also that we get even a very good performance, even with 50, using only 50 particles, in contrast with the standard particle filtering, that we got like similar performance, but even a little worse when we use 500 particles. Other than that, we should emphasize that the particle filter for MMSE diverged for 50 samples, so we didn't have a result for that. Breaking down this a little bit, now instead of average MMSE, we are plotting MMSE over time, but an average over Monte Carlo simulations as well. And we can see an effective sample size here, and also the trajectory, and we can see a big, the MMSE in meters. We can see a big improvement in the performance. So 50 particles with 100 particles and 500 particles, while keeping the effective sample size very similar to what we have with a standard particle filter. Well, just to see also the influence of considering the uncertainty of DGP in the resampling strategy, we changed p-var from 0 to 0.6, and we performed Monte Carlo simulations, and we can see that the average RMSE improved a little bit for the MMSE for a p-var of 0.4, around 0.4, while it kept more or less the same for the map estimation. And this gain in performance here for the MMSE comes with a at the expense of a smaller effective sample size. So we are trading off, well, the trade-off here is like have a little better, a better estimation from MSE, but we trade off with the stability of our filtering strategy. So to summarize our results, we basically apply Gaussian process for particle filtering to improve basically our PDF estimation, which enhanced point estimate of our unknown state of the system, and resulted in more efficient also resampling schemes that resulted in a better usage of a available number of particles in the particle filter. We also showed that our proposal method has a big gap in performance, so it's improved a lot the performance when compared with the standard particle filtering. Future work include providing that our GP is not negative at all, enforcing it, and also providing maybe better resampling strategies for our resampling process, maybe parallelizing it as well. That's all for now. Thank you for watching this video. Please read our paper, and if you want to reach out to hear our contact information, thank you very much again. See you soon.